We're looking here at the doubly linked list node class. Now I've kept the same name of linked list node, but I've created a new doubly linked list namespace. And this is so that we can keep a majority of the code the same, which will make creating a difference between the doubly linked and singly linked list code easier in just a moment. Now the linked list node is pretty much the same as what we saw with the singly linked list, with the addition of the previous pointer. That is the only change we've made. And the doubly linked list class is also nearly identical to the singly linked list class. And to actually show this more easily, what I'm going to do is show a difference of the single and doubly linked list class and just talk about the differences because we've already gone through the singly linked list class in good detail. The doubly linked list class is on the left, with the linked list or singly linked list class on the right. So as we can see just right off the bat, these are very similar classes. The diff structure is visible here on the left, and you can see that throughout the file it's a very small number of diffs. The first diff is the namespace, so we'll skip that. We'll go on to the second. Alright, so our first major diff is in the add first method. And recall what we're doing here is we have a list that before was head pointing to 5, which a doubly linked reference to 7, whose next pointer was null. And what we're going to end up with is head pointing to the new 3 node, which has the doubly linked reference to 5, who's doubly linked to 7, who points to null. So we're adding 3 to the front. Now the previous add first method is all the same. Temp is set to the head node. So temp, at the moment we're down here, is set to 5. Now because 5 was the head node, its previous value was set to null. So 5.previous should now be set to 3. So we have our doubly linked reference. So that's all we're doing here, is we added basically 5.previous equals 3. And because we're adding to the first, it's a very simple operation, and we haven't added any additional complexity onto the performance characteristics of the add method. We've added a new pointer assignment. So let's go to the next difference. And again, this difference is all about managing the previous pointer. Here we're in add last. Now, if you imagine we have head pointing to 3, doubly linked to 5, whose next is null. Well, now we need 5 to point to 7, but we need 7 to point back to 5, and that's what we're doing here. We're saying node, which is the 7 node, dot previous should be set to tail, which at the moment tail is 5 because we haven't yet updated tail to point to 7. So basically we're saying, all right, you're the new tail node, so your previous node has to be the previous tail node. So once again, it's a very simple change that only has to do with managing the previous pointer, and it doesn't change the performance characteristics of the add operation. Let's go to the next change. And here we're in remove first. So hopefully the pattern's becoming clear. The add and remove methods are where we need to manage the pointers, so that's where we're making these changes. And once again, it's all about managing a previous pointer. So in this case, we're removing the first node. So we had head pointing to 3, pointing to 5, although these should be doubly linked references in a doubly linked list. And now what we want to have is head simply pointing to 5, and then 5's previous should point to null. And that's what we're going to do, is we're going to say the new head node's previous must be null. Earlier, 5's previous pointed to 3. That's what we're changing. So again, we're seeing the remove operation has been updated for doubly linked lists, but its performance characteristics haven't changed. And now we'll go here to the remove last. And this is a case where we actually see performance improve. And what's happening here is before, we had to enumerate over the entire list in order to find the second to last node. But now we don't need to do that. The second to last node is tail.previous. If we want to remove the node 7, what we need to do is change 5 to no longer point to 7, but to point to null. So tail.previous is 7.previous is 5. 5.next used to point to 7, but now points to null. So 5.next points to null. And the tail equals tail.previous. Originally tail was 7, so now tail will be set to tail.previous, which is 5, so the tail is now 5. So we've taken an enumeration of a list that has really unbounded size, and we've turned it into 2 pointer assignments. So in the pathologically bad cases where there's millions of nodes in this list, we've improved the performance characteristics dramatically. And let's move on to the last set of changes. In this case, we're in the remove method, and again, we're just managing a pointer. And what we're saying here is that before we had 3 double reference to 5, double reference to 7, which was the end of the list, and we want to remove the node in the middle. We want to remove the 5 node. So on this line, if that's what we're removing, previous is set to 3. Current is set to 5, which means that current.next is set to 7. So what we're saying is 7.previous is equal to 3. And look at that, that's what we want. We want 7 previous pointer to point back to 3. So we're removing the 5 from the middle. And this is the only case we needed to change. So remove first will handle all the pointer management for the first case. And if we're removing the very end, we don't need to manage the previous pointer because they're all going to be correct. We're just removing the next pointer for one object and updating tail. It's only this middle case where we have a change. And that's the last change we had to make in order to convert a singly linked list to a doubly linked list. So for the cost of one additional pointer in the node and a little more pointer management during add and remove operations, we were able to remove the most expensive operation that existed within the linked list class. And that's a really good performance benefit to take for a little bit of overhead. And it also makes the list much more functional. Now as a consumer, my for each will only iterate forwards in the list. That hasn't changed. But once I'm midway through the list, I can manually walk backwards. And that's a very powerful pattern to be able to have introduced. So as we'll see in a few moments, the doubly linked list is so important that .NET's own linked list class is a doubly linked list.